Our two speakers tonight are Yilun Ma and Shishir Dholakia. They're both upper-class undergraduates in our department. Shishir does research mainly on exoplanets. Outside of school and research, Shishir does astrophotography and badminton. Yilun is a third-year undergraduate student that does research on stellar flybys near debris disks and spectroscopic analyses of active galactic nuclei outflows. Yilun also does astrophotography and mainly does nightscape photography. So hopefully after this, if our speakers want, they can share their repositories of all their cool astrophotography photos. But yeah, so the talk tonight, Comets, a Tale of Citizen Science and Research Astronomy. I'll just let the speakers have the floor and you guys can go ahead.
All right, thank you, Stephen, for that introduction. Good afternoon, everyone, and good evening if you're on the East Coast. I know this is Astronomy, but it's happening in the afternoon. But hope everyone is staying safe and healthy, and thank you for being here with us at this very special time of our lives. My name is Yilun, and also we have Shishir over here, and let's say hello. Yeah, and so tonight we're going to be talking about comets and how both professional astronomers and also amateur astronomers, the two community both contribute to our understanding of these amazing objects. All right, so without further ado, let's get started. So comet has been quite a topic this year, actually, in the media and also on the internet. And if you see, I just muted myself. And if you see over here, the Google search of the word comet actually peaked in the month of July. And this is because a great comet named C2020F3, or more commonly known as Comet NEOWISE, actually made its apparition in the sky in July. And here's a picture of it. And it was the brightest comet visible in the Northern Hemisphere in the past 23 years. And last time we saw a naked eye comet of this kind was in 1997 when Comet Hale-Bopp appeared. And that one was even brighter than this one, by the way. And Shishir may talk about that a little bit, some stories about Hale-Bopp. As you can tell in this image, they're just gorgeous. And with that tail sweeping across the sky and also all those like little star background. And it was even more spectacular if you got the chance to actually see NEOWISE in July with your actual eyes. So, and so many people around the globe, they came out to see them, and then thousands of cameras and telescopes were pointing at them. But why exactly do we even care about comets? What are they anyways? And where do they come from? So let's talk about those. So first, what are comets? The American astronomer Fred Whipple in the early 50s actually first proposed that comets are dirty snowballs. Yes, and that's not a comet. That's just a dirty snowball to show what it's sort of like analogous to what a comet looks like. And then this idea was later confirmed. And with more observation and more data coming in as time progresses, some people also call comets as icy dirt balls, depending on like its composition. But I guess whichever name that you prefer, both names are pretty self-revealing, actually. So comets are primarily composed of dust and ice. You can think of this dust as very small particles of rocks, and then it's a very easy concept, I guess. But by ice, I don't specifically mean water ice as we see every day, although water ice is actually somewhat a vast majority of it. Ice is really a general term for frozen gases. So an everyday analog for that would be dry ice. But on Comet, they are, instead of CO2, which is carbon dioxide, this ice could be carbon monoxide, it could be ammonia, it could be some other compounds as well. And when they're approaching the sun, this is our dirty snowball of one of the comets that the spacecraft Rosetta actually had a flyby of. So this is the nucleus. So when they approach the sun, they get heated up by the sunlight, by solar radiation, and this the ice inside this nucleus, they start to sublimate, which means they turn into gas without going through the intermediate liquid phase, and then they start to get burst outside of this nucleus, which is this white plume that you're seeing over there. in this image. And then this gas, then they would surround the nucleus and sort of form a little atmosphere-ish layer, and that's what we call the coma. And then we have the sun over here. The sunlight will exert a radiation pressure and also blows out this solar wind. And then these interactions will then push all of this gas and also the dust particles carried with the dust away from the nucleus, and then they eventually become the tails that we see in the night sky when NEOWISE actually made its apparition. All right, so let's keep going. Where do comets actually come from, and why do people even care about comets? Are actually two questions in one. So in my opinion, comets are all about creation, right? So first, from a pop science point of view, it's about the creation of life. So you may have heard of the concept of panspermia, where comets had brought very primitive form of life onto Earth from somewhere else. Although this idea is very controversial, we do detect organic compounds on the comet as well. So, and also there are also other theories suggesting that comets have brought water, enough water to the young Earth. So there was like a comet rain or something. So that life was actually possible to be born at the very beginning anyways. But more importantly, to astronomers, comets are extremely relevant to the creation of the formation of our solar system. So let's talk about that. Here's how our solar system was formed. So initially, there was this giant molecular cloud, or just a cloud of gas, very dense, cold gas, spreading light years across in the universe. They're just floating over there. And then one day, this cloud decided to collapse under its own gravity. And then as it's collapsing, it becomes hotter and hotter and denser, up to the point where it's hot and dense enough so that nuclear fusion starts. And then our sun is born. But since this cloud at the very beginning has a net motion, like there's a slight rotation of this cloud at the very beginning, as when it's collapsing, the gas gets flattened out as well. And then that forms a gaseous disk around it. And that's what we call the protoplanetary disk, or the solar nebula in our sun's case. And it is from this disk where the planets were formed. Dust particles and frozen gas in the solar nebula, they would agglomerate and stick to each other and form larger and larger particles, and also like other objects in this disk, including planets' cores, and also like what we call the cometary bodies. And an important thing to keep in mind is that these little bodies, these small objects, they share the same chemistry with the disk gas. So because they were formed within, they were basically the materials in the disk, and then they eventually become all these bodies. And then 5 million years later, this gas is blown away, and what's left are just solid particles. But that disky structure, it remains, and which is what we call the debris disk, as you can see in the image on the left. On the right is just an illustration showing there's no gas anymore, and then there's just solid particles. But on the left is an actual image of debris disk. That ring that you see over here, this is basically cometary particles. And we also have one of these in our solar system, actually. And that's what we call the Kuiper belt. And it is located outside the Neptune's orbit, so way beyond our Earth, our Earth's orbit. And some of these Kuiper belt objects, they could be kicked outward by the planet to even farther distance from the sun and end up at locations where the surrounding star's gravity becomes noticeable. And those stars, they will then sort of modify and also affect or shepherd the orbit of these small Kuiper belt objects, and then eventually forming a spherical region at the very outer edge of the solar system. And that's what we call the Oort cloud, which is you see on the right. This diagram over here is not to scale. So on the left, you see is the Kuiper belt. It's just an illustration. And then this spherical envelope around the solar system on the right is the Oort cloud. To put these two regions in scale, we can see this picture over here. Even Pluto's orbit, or like the Kuiper belt, is only just around this little yellow dots in the center of of the image, which is our sun, basically. So Oort cloud can extends to even like 1 to 3 light years away from the sun. But once every often, these particles in Kuiper belt and also in Oort cloud, they will get kicked by either Neptune's gravity when they had a close encounter with Neptune, or by experiencing a flyby of a nearby star. And then the particles would then leave the Kuiper belt or the Oort cloud and start their journey into the inner solar system once again, and then getting heated up and become the comet as we see them on Earth. And so technically, they are sort of like the messengers from the outer system. And it is by studying this, dynamics of these comets and also the planets, and also even the nearby stars, we could infer the evolution of the solar system as a whole. And also, if you remember that I said these particles, these cometary objects, they share the same chemistry with the disk, and that's basically saying they are like time capsules of the history of our solar system, because comets are the least chemically processed object in the solar system. Unlike Earth, our atmosphere is heavily modified. When it was formed, I can promise you there was definitely not as much oxygen as there is right now. So whatever that was in the solar nebula is preserved in the comet. So by studying comet, we could possibly gain the information of the environment from which the planets were formed. Right. And Shishir is going to talk about some of the science that we're going to be conducting with Comet.
Well, so Yilun just explained a little about what a comet is, but how exactly do we know this stuff about comets? So professional astronomers get only one thing from comets, and that is the light. So we need to use the light that we get from comets in order to figure out all of these things that Yilun talked about, what they're made of, how they move through the sky, and what their orbits look like, where they're distributed throughout the solar system, and various other things about comets that we now know. And so in order to do this, astronomers make use of every single property of light that there is in order to figure out what about comets. And so, for example, some of these properties of light are color. There's the source of the light, where the light is coming from. There's brightness, how bright the light is. And there's one more called polarization, which I'll explain in a second. But let's start with the location of the light. So where's the light coming from? Astronomers can use this, and this technique is called astrometry, in order to learn about the orbits of comets. So as soon as a comet is discovered, astronomers will carefully track the comet as it's moving through the sky in order to chart its path. So this image shows how the comet moves over time through the sky, and it's actually showing the numbers correspond to dates, I think in the month of July, as Comet NEOWISE moved through the sky. So soon after the discovery of a comet, you can basically chart the motion of the comet through the sky and then use the laws of physics in order to figure out what its orbit looks in the solar system. And that allows us to predict where it's going to be in any number of days. So once you know its orbit, you can then predict where it's going to be. And then the next property is the color of light. So some of you might be familiar with the electromagnetic spectrum, also known as the light spectrum, right? So it goes from violet on one end to red on the other end. And in fact, some of you may know that it goes outwards in both directions. There's ultraviolet and there's light beyond ultraviolet, and there's infrared and there's light beyond infrared. But for the purpose of this, we'll focus on the light that's visible to our human eyes. And one thing you might not know is that the color of light actually also corresponds to the amount of energy that light carries, or the amount of energy that's required to produce that light. So for example, violet light will require more energy to produce, and red light will require less energy to produce. And this is why, for example, ultraviolet rays can damage your skin, whereas red light is completely harmless to you. Yes, so next slide, please. So in order to understand why this is useful for comet science, we need to take a look at the model of an atom. So this is a simplification, I should say, but it's good for our purposes. Atoms consist of a nucleus with electrons in orbitals around. And so the important thing to know about these orbits is that they're discrete. So there's nothing between 2 and 3. And there's nothing between 3 and 4. And when I say that something is glowing, for example, a comet, what I mean is that the electrons are jumping from a high orbit to a lower orbit. And in that process, they're giving off energy. And so specific atoms will have electrons jumping from higher orbits to lower orbits, and in the process, they'll give off light of a specific energies corresponding to how much that electron has to jump. And so, for example, the energy, this is an example of how hydrogen would look. The jump from 3 to 2 or the jump from 4 to 2 gives off light of very specific colors. So when you decompose this into a spectrum, you get lines in the spectrum that correspond to those specific colors. And this is called the Balmer series. You can use this barcode in order to identify what chemical elements are present in a comet. So next slide, please. So a comet, as I've told you earlier, consists of the main icy chunk and a coma around that. And so by decomposing the light from the coma, we can figure out what the comet is composed of. So next slide, please. Oops. Continue on. I think this is a slide from the past. Ah, yes. Okay, this is the slide I was looking for. So with this knowledge, we can now begin to ask a couple questions about this image that things that you might notice. So, for example, you might notice if you look really carefully that the region directly surrounding the core of this comet is slightly greenish. And you might notice that there are two tails of this comet. One of them is blue and one of them is like whitish, right? So you can ask, why is this the case? Well, when you decompose this light into a spectrum, you can gain an understanding of why this is the case. So as it turns out, when people did this, they realized the ion tail, that's the blue tail over here, is composed of this specific carbon monoxide, this charged carbon monoxide particles that happen to glow in a specific color blue. And the green comes from cyanogen, also which you may know as cyanide, which is toxic here on Earth. But there's this chemical will glow green when exposed to the solar wind. And so by decomposing this light into the spectrum, we can gain an understanding of what comets are made of. And so there are two tails because when the solar wind blows on a comet, the charged particles move because of the charge of the ion of the solar wind, and the dust tail is since there are varying sizes of dust, the dust tail actually extends downwards. It's lighter and it curves as the comet moves through an elliptical path around the sun, an oval-shaped path around the sun. Next slide, please. So to demonstrate sort of how a comet works, I did a little demo earlier where I basically took a piece of dry ice, which is solid carbon dioxide. The useful thing about dry ice is that it sublimates. And so you can, just like a comet, this is how like a solid goes directly from the phase of a solid to the phase of a gas. And I stuck it in front of something that produces a wind of charged particles, very similar to the sun. And so you can see over here, as it's sublimating, that the gas sublimating off this comet is streaming away from the comet. And you can imagine that if this little piece of dry ice were to be swinging through space, you might have a second tail as the material of the comet trails behind and simultaneously is pushed by this solar wind. So you have both your ion tail and your dust tail. And that's why comets have two tails. Next slide, please. This is one more property of light that's not often talked about, but is very informative for comets, and that is polarization. So as it turns out, light is a wave. It's not just a particle. And the direction of the wave can be waving up and down, or it can be waving left to right, or any direction in between. The direction of the wave can tell you something about a comet. So unpolarized light means that all of the different waves are waving random directions. So there's no particular preference for a direction. But as it turns out, reflecting surfaces, when something reflects off a surface, it polarizes the light. And there are also other effects that polarize the light that are relevant for comets. And so this means that once the light reflects off the surface, the wave is only in a specific direction. And this is actually how sunglasses work, polarized sunglasses. So if you ever put on a pair of polarized sunglasses, they're designed to cut out this polarized light, right? So if there's light glinting off the approaching car or from the water, the polarized sunglasses will cut out that reflected light and allow you to see better because there's no glare. And astronomers basically do the same thing. Yeah, next slide. Astronomers basically do the same thing by putting these, like analogous to polarized sunglasses, in front of telescopes, and they use it to see only this reflected light or only this polarized light, and that allows us to figure out what's going on with comets. So this is actually a measurement I've conducted for Comet NEOWISE in polarized light, and you can sort of see in this image, the more brightly colored things are more polarized, so you can see that the core is heavily polarized. And we think that this is because as the comet emits, so Yilun talked about how comets are dirty snowballs. As the comets are emitting these dust grains, those dust grains are aligned and they're polarizing the light, and we can see that in this polarized picture of a comet. Next slide, please. Yeah. So I want to quickly wrap up by saying, so with all of these properties, and including also brightness, we can gain an understanding of how comets, what they're made of, what they're composed of, and all of the different things about comets. But it's not the only way that we know about comets. There's more ways that we'll talk about later. But first, I'll let Yilun talk about the different pictures you might have seen before and how they were taken.
Right. So what Shishir talked about is basically how professional astronomers would be approaching to studying comets. But then you will be saying, okay, I don't work in professional astronomy, and why do I even care about comets anyways? Like they are not relevant to our everyday life. And what can I say? It's like, you're right. I mean, yeah, to be honest, they're not really intimately related to our daily lives. But hey, it would be nice to actually do some astrophotography and actually take some pictures of it. And this is exactly what we do. Like we are, apart from being students of astronomy, which means we're trying to become professional astronomers, we are also astrophotographers, which is you see over here, that's literally me pretending to be taking pictures. I wasn't really taking pictures in this image that you're seeing. So being astrophotographers means we are part of the amateur community as well. And then we image the night sky all the time. And then whenever the weather is clear and when we don't really have to work on homework, which is never really happening. But anyways, I'll talk about like how we image the sky as photographers first. And then I will show you some techniques that how you will be able to do it as well. So I have to admit that astrophotography covers a lot of techniques, and I will only introduce the two basic ones shared by both astrophotographers as well as professional astronomers. So the first one is tracking. So we have to track the motion of the star. So in astronomy, many targets are very, very faint. And I assure you that the comet that you see in the previous pictures was not as bright as it looks like on this photo when you actually see them under the night sky. This is more of like a realistic picture of what the comet really likes when we actually saw it in Lake Sonoma in July. But how do you make a picture like this. You have to collect more photons. You have to make the image brighter. So that means you have to keep the camera shutter open for a really long time to get as many photons as possible, or to collect as much light as possible in a certain interval of time. But that poses a problem. You might be noticing that stars actually, they move across the night sky over a night or something, just like the sun and the moon, they rises and set. But so that means if we're simply pointing the camera, or like if you simply leave the camera stationary, the target will leave trails because of this effect of rotation. And the image will be blurred like this. That's like, so if you see over this comet, you can see none of the, like, you can see like literally zero details in this picture, except for this. Okay, I know there is some objects over there. But there are, to correct for this effect, those ingenious people, instrumentalists, they designed this thing called an equatorial mount. So they actually track the motion of the sky as our Earth rotates. So if you see in this previous picture over here, there's a star in the center of all the circles that seems to be not moving so much, and that's the star called Polaris. What the equatorial mount does is that it aligns its rotation axis to the Earth's rotation axis, which means it's just basically pointing to Polaris, and it just rotates in the same rate as the Earth does, but just to the opposite direction. So it's following a single object in the sky over a long period of time, and that makes a long exposure possible. If you see on the left over here, that's basically the telescope of Shishir and his twin brother tracking the night sky. And also in professional astronomy, people do track the sky as well. As you see on this small video that you see on the right, that's the Keck telescopes on the summit of Mauna Kea. They use a slightly different mount, but the idea is the same, just to make sure that the image is not blurred and the rotation of the Earth is actually counteracted. So with this tracking technique, we had an image like this, and then with tracking, the image turned into something like this. It's much sharper. We see a lot more detail in this picture, and that's what we want as like a good astrophotography photo. And the second technique is called a stacking, because longer exposure is not enough for us to get a good photo. Because there is this thing called noise. Noise is basically this little grainy structure that you see on the image on the left you see over here. Those are just some random fluctuations of like brightness in each pixels, and they are random, like they are distributed randomly across the entire image. And you can see like the image is kind of like blurred with all of this noise, and a lot of small details are actually buried deep within and is not able to be seen. But this is definitely not a good photo. We don't want to look like this. Like it's just, to me, I would use the word disgusting for such an image. But how are we going to deal with that? This is where stacking actually comes in. So we take multiple photos of this kind, of the same object, and then with the tracking method that we discussed before, and then we will let the computer to put all of these photos on top of each other, literally just align them, like make sure that the stars are in a good position, and then align them and then stack them on top of each other. And in this way, since the noise is random, they will get smoothed out, and a lot of details buried within will be revealed once again, as you see over here. So say, for example, there's a little change in brightness of the cloud over here, like on this region of the sky, that you can't really be seen in the unstacked image. And now, since the noise is smoothed out, we have successfully enhanced the detail, as you can see in the right over here. So, and also, this is actually how people image other targets like galaxies, exoplanets in the professional field as well. So I work in this group in Berkeley that directly image exoplanets. So we take pictures of exoplanets. And it's almost exactly the same procedure as what I just explained to you. And a very interesting story is that when I was a freshman And then I was trying to get into this group, and I met the faculty who was in charge of that. And then he was asking me, oh, have you ever taken any astro classes? And I was like, no. And then he was a little bit disappointed. And then he asked me, oh, I heard that you do astrophotography. I think you put that in your email that you sent me. And I was like, I do. And he was like, oh, do you know all this stacking? Do you know all this tracking thing? And I was like, yes, I do. That's what I do pretty much every night. And it's like, okay, you're in. And then that's how I actually got my first research project, which is just funny. And at this point, you might be thinking that astrophotography is hard and you need a high quality telescope and all those very complicated and expensive equipment that you might have like read about on the internet, and also like you've seen like on these time-lapse videos that we're showing you. But really, that's just not true. I seem to get a lot of like perception that my friends think astrophotography is hard. Like everyone thinks astrophotography is hard, but that's not the case. There is this field of astrophotography called the nightscape, and where neither tracking nor stacking is necessary. A camera or even a phone camera will suffice. And with the simplest equipment possible, you're able to image the night sky, even the next great comet when it comes back. Say, for example, over here, this is actually an image taken by Shishir and Shashank. So this is an image taken by a phone camera. And how does this work? So a wide angle field of view is what we'll be using because you can't really hold a phone camera for like a really long time. And don't zoom in if you're on the phone. The idea is the same. We want to make long exposures, keep the shutter on for a long time, and collect as many photons as possible when the shutter is open. And there are some steps to take. First, you have to station your imaging device. Make sure it's not moving. Otherwise, your image will get blurred like straight away. You can put them on the ground or like lean it against a wall or like even against your vehicle or something. But just make sure it's stationary and it's safe. Just stay over there. And then also make sure that there is no sort of like vibration on the ground or some other stuff. Like just don't jump around when you're actually taking pictures. And then there are, so a normal phone, like the default camera setting in your phone wouldn't necessarily work, but there are a lot of apps on the internet that can literally have you set all of these exposure parameters on like aperture, ISO, all of these numbers. So these are just some tiny little details that you have to sort of taken care of, and then make sure you set the exposure time to 30 seconds. So it's collecting photons during that 30 seconds, and set the aperture as the largest. So just think about like there's like this little hole where all the light is coming in, and the larger the hole, the larger this hole is, the more photon you will be collecting in a unit time. And also set this like the ISO to like the largest. And it's just a parameter for like how sensitive your camera is, or like how bright your image is in a dark environment. And then there, after all of these settings, you can just hit go. And then wait for like 30 seconds or something, and then bang, you have your first astrophoto over there. It sounds a little like now that I'm saying this, it sounds a little bit like quite easy, but there are some subtleties, but it could be overcome. Everyone has their like first time taking astrophotos. And then you can just post them onto your social medias and get like likes and wows and all of those comments. And yeah, this is how astrophotography is done. And keep in mind that you can do astrophotography as well, even without a telescope.
All right. So Yilun just talked about how to produce pretty pictures. I want to say that, so he's right. You can pretty much start doing astrophotography without any equipment at all. But there's actually a community of dedicated amateurs who spend their nights going outside, taking their telescopes out, and photographing the night sky for fun. And one thing that's very interesting about comet science is that this exact community happens to contribute to science as well. And comet science is a great example of that. And One example is Yilun mentioned earlier the comet Hale-Bopp. Some of you, if you are old enough, you might remember one of the last great comets was the comet Hale-Bopp. It became extremely bright, and it was actually named for two people, Alan Hale and Thomas Bopp. And these two people, one of them, Alan Hale, was actually a professional astronomer. Thomas Bopp was an amateur astronomer, and they both happened to be taking a photo of this pretty object in the sky called a globular cluster. And they both noticed at the same time that there was this faint fuzzy blob that was moving in their image between photos. And they both realized that, okay, wow, this is not something that's been reported before. This is probably a new discovery. This is probably a comet. And they both reported it, and as a result, the comet was named after both of them. And then, very unexpectedly, it became extremely bright. It became one of the brightest comets in the sky, and it's been immortalized now because it's one of the great comets of the 20th century. So this is a great example of how citizen scientists have contributed to comet science. Now, if you ever get a chance to photograph a comet, one thing that you can do is estimate the brightness of the comet from your photograph, and there are ways to do this. You can visit this link called cobs.in. But basically, this is an example of measurements made by amateur astronomers coming together to form a graph of the brightness of this comet NEOWISE over time. And as I mentioned earlier, comets are notoriously difficult to measure the brightnesses of. And it is extremely scientifically valuable as well because we can gain an understanding of how comets move through the solar system and how much light they're reflecting. Also, measuring the brightness over time of comets can allow us to, because as comets rotate through space, right, they reflect different amounts of light. So measuring the brightness of comets over time allows us to measure the rotation rates of comets. Although this is typically a measurement conducted by professionals with more sophisticated equipment, understanding how the brightness of a comet changes over time is something that is done by amateurs as well. And this is a valuable contribution to science. There is also, so even if you just upload one of your images to the internet, you can contribute to science valuably. So there was I usually don't quote research articles in public talks, but there's one paper that does a particularly good job of showcasing how citizen science can be used by the professional community. Next slide, please, Yilun. I think, okay, so I'll talk about this first. This guy is named Borisov. He's another discoverer of a comet. He's an amateur astronomer who discovered a more recent comet in the 21st century. He noticed a comet in one of his images and reported it, and the comet actually became relatively bright. And we've only had one great comet in the 21st century, but which is NEOWISE. And we're waiting on more. But it's undoubtedly true that amateurs may well be the ones to discover that next great comet. Next slide, please. So this paper basically took a bunch of images of comets, just taken by regular people like you and me, or people who went outside and took photos with their little camera of a comet. It took all of these pictures off the web, and it tried to use that in order to figure out how the comet moved through the sky. So this was not Comet NEOWISE, this was a comet earlier, but professionals are currently doing this on comets like Comet NEOWISE. And so it's I can quote from the paper directly because the paper puts it really well. The biggest lesson is that there's an enormous amount of information about astronomy available in uncurated, non-professional images on the web. Perhaps this is not surprising given the large amount of telescope aperture and detector area owned by avid photographers. We have learned that we can do high-quality quantitative astrophysics with images of unknown provenance on the web. Is it possible to build from these images a true sky survey? We expect the answer is yes. So they're saying that the contribution of images from the general public is very valuable to science, and this is indeed this is true. So, in conclusion, comets are are, as Yilun mentioned, they're time capsules. They allow us to take a look back into the early formation of the solar system. They allow us to look at how the Earth looked early in its formation, and they give us tantalizing clues about how life originated on the Earth. But more importantly, perhaps, the science of comets prove that science is done best when professional academics and citizen scientists unite in the common goal of understanding the universe better. Thank you.